Hello everyone, and thank you for your listening. I'm honored here to introduce our work about the maximum weighted independent set problem. And as you see, we have four parts to go through. And before we get straight to our point, we are going to learn some essential concepts so that we can better follow our work. And first, we talk about what the maximum independence is. The maximum independence set problem originates from the graph theory. And independent set means each node pair in this graph are not adjacent. The maximal requires that this set cannot extend anymore. And based on this, the maximum independent set denotes the set that has the largest cardinality, which means it has most vertices. And take this graph as an example. It has two maximal independent sets, as distinguished by two colors, and that is the blue and the orange. The orange one, we can see that it has three elements, while the blue has only one. And as a result, we can say that the orange vertices together form the maximum independent set of this graph. And for simplicity, we will use MWIS to represent the maximum independent set. The MWIS problem is an important topic because it strongly relates to many other well-known problems, and such as the maximum click and the minimum vertex cover, and which are also NP-hard problems. It has been proved that the MWIS problem is equivalent to these problems. Look at these two small graphs. We can easily see that the maximum independent set of G is equivalent to the maximum click of G's complementary graph. And for a single graph, the maximum independent set and the vertex cover set are complementary. And these problems are hot topics in graph theory, and the solution to one of them will also contribute to progress in the others. And thus, the MWIS problem really deserves great attention and our deep research. However, there exists a problem in the real world that cannot be modeled by MWIS, despite of many similarities. The problem is that in the classical network interference model, the adjacent transmitters cannot transmit simultaneously to avoid data loss. And if an efficient dispatch algorithm is wanted to maximize the total throughput of this network, and with the transmitters as the nodes, and the communication links at the edges, every vertex assigned to a weight according to its throughput. This problem falls into finding the independent set with the largest weight instead of the largest cardinality. So this is a weighted and generalized version of the MWIS problem. But it is lacking in research compared to the traditional problems, which also accounts for our attention to it. And in this slide, we formally introduce the maximum weighted independent set problem. For simplicity, we will call it the MWIS in the following sections. The traditional MWIS problem focuses on the number of the non-adjacent vertices, and while our weighted case puts attention on the maximization of the total weight, and therefore here we define the maximum weighted independent set by the maximal set with largest weight. And let's take an example as well. Here, every vertex is assigned a positive weight. The meaning of this weight depends on the concrete scenario. And in this instance, the maximum independent set will take the orange vertices as a solution. And however, this single vertex is actually the solution for our weighted problem. So we can see that the solution to the MIS is not true of our MWIS problem. And in the next section, we'll introduce some existing work and framework so that you can understand our problem in a comprehensive manner. And initially, the solution can be divided into 3 branches. And as a matter of course, lots of research was devoted to computing the exact answers. And among them, the most famous is a branch and reduced paradigm, whose complexity is bounded within 1.2 to the n. And n is the number of vertices. And the secondary branch is to approximate the answers within a specific vector. But it turns out that it is also NP hard as well. The last and meanwhile the simplest is to use a greedy strategy to get the answer. It attains a linear time cost at the expense of the accuracy of the result. And combining the techniques previously mentioned, the reducing and peeling paradigm currently is the state-of-the-art solution to the maximum independent set. It consists of 2 parts, and that is reducing and peeling. In the process of reducing, certain vertices can be removed accordingly via the reduction rules, and this transformation retains its optimality. In other words, owing to these rules, we can determine whether some vertices should be included or not. The reduction serves as a very important role to reduce the time cost by including or excluding the vertices. But rules come to effect under certain conditions. After several rounds of reductions, this graph is sure to be stuck in a frozen situation, where no reductions can be applied to, and thus, we intuitively break this tie by taking out the vertex with highest degree, so that reductions can proceed again. And this alternate process will go on iteratively until all vertices are removed. And in the rest part, we mainly talk about our reduction rules. And following the reducing and peeling paradigm for the unweighted case, we try to design reductions tailored for our weighted graphs. So the first rule, the single vertex reduction, it tells that if the weight of a vertex is not smaller than that of its neighborhood, and then this vertex is surely included in some independent set. This can be proved by a simple cut and paste method, and that is to say, suppose that several neighbor vertices of V are in some independent sets. We can cut these vertices out and paste V into set with vertices keeping independent. As shown by this picture, there's no chance that these orange vertices appear in some solution together, because green vertex itself can replace them by virtue of its heavier weight. Because because 3 plus 6 plus 7 plus 12 is smaller than 36. And when we think, when this single vertex reduction works, we open our minds, what if two vertices? And is there a possibility that two separate vertices can appear in some solution at the same time? And through our observation, we can confidently tell you yes. But I guess we may ask, what about more vertices, like 2 or 3, or so on? And this is a good idea, that small vertices combination comes with fast-growing time cost. We better handle cases up to 2 vertices. So following the same rationale, here comes our second reduction, inspired by the first one. But we know enhancement brings new constraints. It is required that this reduction has to come after the single vertex reduction. Otherwise, the correctness is not ensured. Also, we take a look at an example. These two green vertices cannot trigger the single vertex, since their own weights are smaller than that of their neighborhood. But as a whole, they can be reduced by our new reductions. You can calculate. You can do a calculation. And however, in fact, we actually have at most n squared pairs to handle. And do we need to compute all of them? And if so, n squared can be quite large, with increasing scale of the graph, and which makes it impractical to handle. But don't worry, with the following theorem, we can narrow the searching space dramatically. This theorem tells us we only need to consider vertex pairs sharing at least one common neighbor. And why? Because you think, after cleaning by the single vertex reduction, the weight of the remaining individual vertex is certainly smaller than that of its neighborhood. For example, look at this graph. Both V1 vertex V1 and V2 are smaller than that of their neighborhood. You can see 4 is smaller than 18 plus 9, and 6, and here is 5 plus 7, that is 12. 6 is smaller than 12. And they don't share, and also they don't share any common neighbors at all, and which result in a smaller weight compared with their neighborhood as a whole. And thus, by no means two vertices as a whole can have a greater weight if they don't share neighbors. And this is a powerful pruning strategy used in our experiments. At last, let's check out the performance. You can see that we will compare in the 4 aspects, and as regards to the time cost and the memory cost. You can see that we have an apparent improvement. And in order to confirm effectiveness and efficiency, we designed 2 indicators, and that is the set precision and the weight precision. The set precision reveals the percentage of the common vertices shared by the exact method and our proposed method. And the weight precision shows how close our weight approaches the exact solution. And look at this table. We see that these 2 algorithms take much less time cost. You can see that. And DD2 ensures a good weight precision quality, despite of some loss in the set precision. And another issue we emphasize is the pruning ability. The more vertices we reduce, the more accurate result we will get. We can see that these two methods work well in most instances, except in this one, and which results from their densities. So totally, we can conclude that our framework improved performance as expected, and graph with high density is remained to expect more efficient method. So in future, we plan to develop more new rules that can cope with dense graphs and improve current pooling strategy for further enhancement. And that's all for this presentation. Thank you again for listening.